All right, here's tape 1 of ME360 video presentation number 1. We're gonna go ahead and jump right into it by reading the problem statement, highlighting things that are important. So, water flows over a flat surface at 4 feet per second. As shown in the figure, a pump draws off water through a narrow slit at a velocity or at a volume flow rate of 0.1 feet cubed per second per foot length of the slit. So when it says per foot length of the slit, that means going in and out of the page. That's how it's the slit is measured through the dimension that goes in and out of the page. Assume that the fluid is incompressible and inviscid. Inviscid is important because that means that along the wall, the velocity is 0 and can be represented by the combination of uniform flow and a sink. So we will be working with the uniform flow and sink streamline functions. Locate the stagnation point on the wall, point A, which is shown here, and determine the equation of the stagnation streamline. So the stagnation streamline is shown here. How far above the surface H must the fluid be so that it does not get sucked into the slit? So H is shown here. It's the height of the stagnation streamline, and anything below it will get sucked into the slit, aka the sink, and anything above it will not. So we should start with the streamlines for a sink, a uniform flow, and a sink. So if we look at my notes, we have for a uniform flow, the streamline is uy, which is the y component of the velocity, which is also equal to r sine u times r sine theta. R sine theta comes from, if you recall, when converting from cylindrical coordinates to Cartesian, y is equal to r sine theta, x is equal to r cosine theta, and so we just plugged it in for y here. And also, the stream function in cylindrical coordinates along the radial and tangential directions are shown here. So this will be used for the sink, but let's go ahead and talk about the streamlines. So because it's a combination of the two, we know that the streamline, the total streamline, which we're just going to call the streamline, is equal to the streamline of the uniform flow plus the streamline of the sink. It is the sum of both of these. So, like we said here, the streamline for a uniform flow is equal to u times r sine theta. And then the streamline for a sink is shown also in my notes. Is going to be, for a source, it is positive q over 2 pi times theta, but for a sink, it's going to be negative. So, minus q over 2 pi times theta. So here is one of our main expressions that we will use. So that's for the total streamline function. Alrighty, next step is to go ahead and hold on. Right. So we're gonna go ahead and take a look at back to how our streamline functions relate to tangential and radial velocities, because we're given information about the velocities in the problem statement. So the most important one is here. Well, I mean, I guess we're going to use both of them. So velocity in the radial is equal to 1 over r times the derivative with respect to theta of the stream function. And then velocity in the tangential is equal to the negative derivative with respect to the radius or radial direction. So we're going to go ahead and replace our streamline function here in both of the equations. So this is going to turn into VR, velocity in the radial, is equal to 1 over r times the derivative with respect to theta of u times r sine theta minus q over 2 pi times theta. This one here is going to turn into v sub theta is equal to negative derivative with respect to r of u times r sine theta minus q over 2 pi times theta. All right, so we have VR. Once we distribute this into here and into here, is going to give us, I'll write it out, 1 over r times u times r times d over d theta of sine of theta minus q over 2 pi. These are constants. This here's a constant and this here's a constant. That's why it's taken out of the derivative. D over d theta of just theta. All right, so that's going to give you derivative of sine theta with respect to theta is cosine of theta. Derivative of theta with respect to theta is just 1. So that's going to give you 1 over r times u times r cosine theta. So this is going to get distributed. It's important to have your brackets set up correctly. Minus, we said this turns into 1, so q over 2 pi times 1 over r. If you notice, these r's will cancel out. This r stays there. So just to write it a little bit more neatly, VR is equal to, velocity in the radial is equal to u cosine theta minus q over 2 pi r. Here is another important equation. And we'll go ahead and do the same thing with v sub theta. Velocity in the tangential direction is equal to, this gets the derivative with respect to r gets distributed here. So u sine theta are constant, are constants to that derivative, and then all of this is a constant to this derivative. So when this gets distributed there, it's going to equal 0. Let's go ahead and write it out. Minus d over dr of, minus minus u sine theta times d over dr of just r minus d over dr. When you distribute a negative with the negative, that turns it into a positive. So plus d over dr of the constant q theta over 2 pi. Like we said, this turns into 0. And so you have velocity in the tangential direction is equal to minus, this is going to turn into a 1. U sine theta times 1. There you have it. We now have equations relating, we got the equations that related the streamline function to velocity in the radial, velocity in the tangential, which we will be using to solve for our equation for the stagnation streamline and the location of the stagnation point on the wall. So we will take these and use a new piece of paper. Okay. The next step, now that we have these, is to go ahead and solve for theta and, okay. We're gonna solve for r and theta because r is gonna be the distance here away from the sink. Determine the equation of stagnation. Yeah, locate the stagnation point. So we just have to give a distance here, and this is going to be r there. So let's see. Let's go ahead and solve for r. V sub r is equal to u cosine theta minus q over 2 pi r. Oh, right. Okay, so we need to define certain things that happen at the stagnation point. So at stagnation point, velocity in the radial direction, Vr, is going to be equal to 0. If you notice, when it's stopped here, the fluid is not going to be moving left or right in the radial direction. And also, theta will be equal to 0. Or no, because of because of inviscid, like we said, the velocity at the wall of 0 is equal to 0 degrees, or v of 0 degrees is equal to 0, which we can check using this equation here, which we can find our theta using this equation here. So if we know that velocity at the wall is equal to 0 due to the fluid being inviscid, we plug in 0 to this equation, equal to negative u sine of theta, solve for theta, which means we could divide by negative u, which would give you a 0 again, and then sine of theta is equal to 0, sine of 0 is equal to 0, theta is equal to 0 degrees. All right, so then like we said, at the stagnation point, the radial velocity here is going to be equal to 0. So rewriting this equation and plugging in both 0 for Vr and 0 degrees for theta, we have 0 is equal to cosine of 0 is going to be 1, so this is just going to be a u, minus q over 2 pi r. So if you can see, now we're left with a distance that we can solve for, and we have a value for u and we have a value for q that are given in the problem statement. 4 feet per second, that is our u, and the volume flow rate of 0.1 feet cubed per second is our q. So something important to note, we're not going to be plugging in 0.1 feet cubed per second for our q, because if you notice, this is half of a sink. So this flow rate that we're getting here is due to half of a sink, when in the equation we need to be plugging in the actual sink flow rate if it were to be coming in from 360 directions as shown here. So pretend you split this in half, and that's what we have. That's the flow rate that is given in the problem. So whenever we plug it into the actual flow rate equation here, it has to be multiplied by 2 because this is only half of a flow rate. So we can plug in our values now, or we can solve for r first. Let's go ahead and solve for r first. So this, like we said, is going to be 0.2 feet cubed per second because it's double of this one, accounting for the other 180 degrees, which are not accounted for in this situation. U, like we said, is equal to 4 feet per second. So let's go ahead and solve for r. We're going to bring this around to the other side. We're going to have q. I didn't mean to hit the camera. We're going to have q over 2 pi r is equal to u multiplied by 2 pi r. We have to divide by u 2 pi, divide by u 2 pi. We have r is equal to q over u 2 pi. plug in values, like we said, 0.2 feet cubed per second over 4 feet per second times 2 pi is going to give you, quick math on the calculator, 0.2 divided by 4 times 2 pi. We have 0.00796, we'll call it, feet to the right of the sink. So if we want to draw this out, this distance here is 0.00796 feet, which answers the first part of the problem. Locate the stagnation point on the wall. Now we need to determine the equation for the stagnation streamline. So R is equal to this, theta is equal to 0 degrees. If we plug that into our original streamline function here, theta is 0, that'll give us a grand total of 0 for our streamline function. Therefore, to find the equation of this streamline, plugging in the points that we have for the stagnation point. So now we will be solving for the stagnation streamline. So to do this, like I said, we bring back our streamline function. 0 is equal to the rest of this. So u r sine theta minus q over 2 pi times theta. So for random theta and r variables, we're going to go ahead and try to find a function in terms of y. And if you recall, when switching from Cartesian to cylindrical coordinates, y is equal to r sine theta. So we can replace y here, which gives us 0 is equal to u times y minus q over 2 pi times theta. We solve for y, bringing this to the other side, dividing by u. So this will come over here, become positive, divided by u, which will give us that y is equal to, so q over 2 pi, theta can go up there, divided by u. Oops. That is the equation of the streamline function. So now that we're going to be looking for h, which is in terms of y in that same coordinate system, h is in the y direction. It's going to be, there's two ways to solve for this, and one of them is you just have to kind of look at it and think of it logically. It's easier to do so when you rewrite this as q over 2u times theta over pi, theta being in radians. So which theta is going to give you the maximum y value here in your function? So we have only from 0 to 180 degree option. So you plug in things that are less, or numbers that are less than pi radians, you're going to give a fraction here, which is going to give you less of a number, or which is going to decrease the y value. Or you can see that pi is going to be your greatest outcome for this equation. So it's going to be your max h. It's going to be the h value when you plug in pi. This is also just looking at it logically, but another way to go about this is in terms of continuity. So we know that if this was a control volume, and it followed the stagnation streamline. We know that the mass flow in has to equal the mass flow out. In other words, continuity gives you, okay, right. So let's say we plugged here. Let's say we plugged in pi for theta. That's going to give you a 1, and then you plug in your regular values. So these are going to cancel out to 1. And then y is equal to q, which is 0.2 feet cubed per second over 2 times 4 feet per second. 0.2 divided by 2 times 4, 0.025 feet. So in terms of continuity, m dot in is equal to m dot out. Rho a v in is equal to rho a v out. Area velocity. And so one thing that we need to recognize is that area is one component of the area is the dimension going or the plane going in and out of the paper. So we're going to assume that is equal for both the inlet and the outlet. And we're also going to assume that, or we don't assume this, we know that the fluid is the same at the inlet and the outlet, so rho can cancel out, which gives you AV is equal to AV. So the component of the area, which is going in and out of the page, can be canceled out in both of these, which would be the length. Therefore, we have H times U, this being the component shown, H times the flow rate in is going to be equal to Q, or the AV that we were given here. And in this situation, we do keep the problem statement flow rate because we are just looking at the left side here, the 1/2 of the sink that we care about. Therefore, we have that H is equal, or yeah, we can rewrite that as H is equal to Q over U. Plugging in the values that we have, 0.1 feet cubed per second and 4 feet per second, gives us a grand total of 0.1 divided by 4, 0.025 feet. So if we want to write this out, this distance here of H is 0.025 feet. So like I said, we can use the streamline function that we derived to find this H based on the R and theta that we found from our streamline functions. Those tell us that the streamline function is going to be equal to 0 at the stagnation point, which allows us to find for other variables, theta and R, to find the stagnation streamline in terms of y. So yeah, we use this just kind of thinking logically, which theta is going to give you like a ratio to multiply by this constant value to maximize your y, which is h, or h is in the y direction. So to get the max y, which ratio of theta to pi, theta being in radians, is going to give you that. And we only have 180 degrees to work with here. So of course you plug in pi because that's going to give you your maximum ratio. It's not going to be a fraction, it's going to be 1 times this constant here, which we have values for. And that'll give you your h value for height of the streamline function. Or you can think of it in terms of continuity once you know that this here is your control volume and your mass flow in has to equal your mass flow out. So there it is. I believe that is everything that the problem statement asks for, and that is it.